Good afternoon, everyone. Next section will start. Before next session, I'll introduce our speaker. The next session speaker is Dr. Mubarak Mujawar. He is faculty member of Department of Electrical and Computer Engineering, Florida International University, Miami, USA. His research interests are the areas of wearable sensors, IoT devices, micro and nano fabrications, additive manufacturing of engineering materials, and low temperature plasma technologies. He has published over 30 research articles in this area. Dr. Mujawar is also involved in engineering education research, and he has a keen interest in creating acting and collaborative learning environments for large classrooms. He is an active member of IEEE, Institution of Physics, American Society of Engineering Education. Dr. Mujawar received his PhD in Plasma Science and Technology from Dublin City University, Ireland. Before joining FIU, he worked as a postdoctoral research fellow at Laser and a Plasma Application Group, Trinity College, Dublin, Ireland. So I welcome Mubarak, sir. Sir,
Thank you, Dr. Kushwa, for introduction. Hope I'm audible. And for organizers to for inviting me to this faculty development program at IIIT Pune. In today's session, we are going to talk about the fundamental building blocks of IoT, which is essentially known as sensors. So I just actually drive you through the sensor, what are sensors, then we might actually take a couple of examples of sensors, and then I will describe some kind of advanced sensors which are being researched at my research group. Okay, so let me share my screen with you and we'll start then. Give me a minute. Okay, so the title of today's talk is Sensors, the Things in IoT. Before we start today's session, I just want to briefly mention about my university, my department, and my research group, and then we'll start our discussion. So I work at Florida International University. It is located in beautiful city of Miami, at the south coast of United States. It is one of the top 10 largest public research universities in USA. Also, it is one of the youngest universities to achieve the R1 Carnegie Mellon research status. We have so far almost 42 programs which are in top 50 in public universities, and our university is also one of the preeminent universities in the state of Florida. So far we have, this year, we have almost 55,000 students enrolled, and we have a very active network of about 200,000 alumni. One of the highlights of our university is that since it is located in Miami, we have the underwater research lab, and that is the only research lab owned by any of the universities. Now, as I mentioned, the name of my university is International, and we have chosen this name International with specific things in our mind. Since the university is located in Miami, it is multicultural, multilingual. We have a very vibrant population who speak Spanish, who speak German. We have large population speaking Hindi as well. So it's really multicultural and multilingual city. We have students from almost 125 countries, and we have almost 60 faculties from across the globe. We also have some international programs. We have very active study abroad program in China. We also have active participation in Erasmus Mundus programs with European partners, and we do have some partners in India as well. Speaking of my department, Department of Electrical and Computer Engineering, it is one of the fastest growing department in the nation, in the United States. Right now, it is number 13 in the number of BS degrees awarded by school in computer engineering. Number 14 in based online master's degree programs in engineering. And number 29 in providing BS in electrical engineering degrees to our students. So it is quite high ranking, and most of our students do get jobs in various national labs and private and public sector. We have very vibrant programs at FIU and at the Department of Electrical and Computer Engineering. We are the first to start the BS program in Internet of Things. And perhaps right now, there are only 2 universities which provide this BS in IoT program, and FIU, my university, started this program in 2018. We also have fully online BS programs in electrical engineering, computer engineering, and IoT. And beginning spring 2019, we have everything online. So we were fortunate that during this pandemic situation, we didn't have any problem with reaching out to our students or making new programs or making some curricular changes. We are running smoothly even during this pandemic situation. We also have very active MS program in network security and in cyber security as well. Some of the areas of research are into advanced microelectronic packaging, integrated nanotechnology, biomems and microsystems, where I work. Then we also have some kind of SMT, advanced processing, network, communications, power, digital signal processing, RF and microsystem. Rather, ours is one of the largest departments doing research in RF and microwave systems. We are also into energy cybersecurity, machine learning, AI, and big data. Now, coming to my group, I work at, I'm associated with other biomems and microsystems group, and our focus areas are into the areas of advanced micro and nano fabrication. We also work in physical MEMS, and part of the work which we do in this physical MEMS section will be described today. We also extensively work in sensors and sensing systems, especially biosensors. We work in IoT, Internet of Things, and IOMT. IOMT means Internet of Medical Things. So our focus is more towards bio and medical things. Along with that, we also have engineering education interest. I personally, I am actually member of a couple of engineering education groups led by IEEE and APS, American Physical Society. Right now in our team, we have almost 25 members. We are 2 faculty members. We have 5 postdocs, 6 graduate students, and 16 undergraduate students. And 50% plus students are underrepresented minority students. So either they are women, they are either African Americans or Hispanic Americans. So the group is quite multicultural. We have students from different nationalities. We have students from Argentina, from Brazil, from Jamaica, from France, and of course, like we have students from India as well. Rather, we have like many students from India. Okay, so let us start with today's module. We'll talk about what is IoT. We'll just briefly look at what is IoT. I know, I'm sure in the afternoon session, or like in the previous session, you might have looked at IoT and different realms of IoT, but I'm just going to mention it in few minutes, and then we'll actually start with our sensors. So now, whenever I think of Internet of Things, I think of Internet and things. We are very well aware of Internet, but we always get confused between what are these things. And that's why there is a nice definition of IoT. And rather, I would say, IoT is such a fascinating area where everything you see, everything you feel, everything you touch can be part of IoT. And that's why we say that IoT is all about connecting the unconnected. And that is what I have in the next slide. So the basic premise and the goal of IoT is to connect the unconnected. Any object which is not connected to computer network, our aim is to connect them to the computer network or internet so that these objects, these things will start communicating, start interacting with people and with the other objects. And if we have these objects talking to each other, then we'll have plethora of things which we can do by leveraging these advances. For example, just think like we have a drone which is delivering goods to your doorstep. We have self-driving cars, for example, or we might have some of the technologies at home, for example, smart refrigerator, which is ordering grocery on its own. All these things are possible with IoT. And with the advent of now 5G communication, these things are going to go forward very rapidly. So this word IoT is not new to us. We started thinking about IoT, we started connecting different things to internet almost 30, 40, 50 years ago. And the word IoT, however, was coined very recently. We started using it in 2008 and afterwards, when the number of things connected to the internet started growing exponentially. There was a person in Procter & Gamble, his name is Kevin Ashton, and Kevin actually coined this term, Internet of Things, when he was actually looking at how he can actually change the supply chain of his company and how we can use supply chain for actually getting some more profit by connecting it to the internet. And I always quote this and I always mention it, that he was quoted as saying that in the 20th century, computers were brains without senses. They only knew what we told them. So that is the key, that earlier, like the computers did not had any brain. They had brains, but without senses. They didn't had any sense. And those senses are now actually being pushed towards computers using the IoT technology. And I often always talk to my colleagues by saying that, like, I don't work in sensors, but I work in sense making. Our shift has been from sensors to sense making by using IoT technology. So as we are all aware, and we have all gone through this evolutionary phase of internet, we have actually started using internet at almost for last almost 30 years, 30, 40 years, 30 years in India and 40 years in Western worlds. And initially, when we started internet, we just had access to emails. Then came Yahoo and Google, and we had access to web browsers and web search engines. So in initial phases, we were using internet just to have some kind of connectivity, just to have some kind of digital access. After some time, around 1995 to 2000, we started using internet for digitizing our business. We started using it in e-commerce. We started using it in digital supply chain. We started using it for different collaborations. And that phase was the network economy. In 2003, 2005, we started having some kind of immersive experiences. We started using social media. We had smartphones. We started actually using smartphones for different connections. We started using cloud. We started voice over internet protocols for communication. So that was an era, or like that is the era which we are still living in, is the immersive experience, where we have more and more digital interactions. Rather than having human interactions, now there are more digital interactions. So this is due to the advent of the internet and advent of the uh, era of intelligent connections. And now we have the era right now, which is the era of Internet of Things, where we are trying to digitize the entire world. We're trying to connect people, we're trying to connect processes, we're trying to connect data, we're trying to connect things. So everything we can think of is getting connected to internet. And many of the devices which can connect to internet are becoming widely available. For example, this one, we are using wearable devices, we are using Arduino Uno, we are using glucometers, we are using Fitbit. All those things are IoT devices, because those are the devices which are connected to internet, which are actually communicating with each other, with the people, with the processes, and trying to get some sense out of that. So this number of devices are increasing exponentially. In 2002, 2003, when we actually started using internet for commercial applications, we had very few connected devices, almost none, and our population was almost 6.3 billion. In 2008, we had an inflation point. So in 2008, we had number of devices equal to number of human beings. So every person had access to the device which had got some kind of internet connectivity, and number of devices and number of people were almost the same. After 2008, however, there was a rapid rise in number of devices which were connected to internet. And now in 2015, we have almost 8 to 10 devices per person. There are 8 to 10 things per person which are connected to the internet. For example, right now, I'm wearing Fitbit. I have my cell phone, I have my iPad, I have my laptop, my car has got internet connectivity. So I have many, many devices right now which has got internet connectivity. However, the population has not increased that much. Okay, let me just see if there is anything. Okay, that's fine. Okay, so it is expected that by 2025, in next 5 years, we will have almost 100 billion objects connected to the internet, and it is expected that we will be either saving or generating in profits almost $19 trillion. So there is huge money involved into the business of IoT, and there is a lot of scope in doing research. For example, as number of devices are increasing, there is a threat. So like there are some concerns about security. There are concerns about providing proper bandwidth. There are concerns about making them more wearable so that we have more access to them. So all the challenges we have to address in next couple of years so as to actually ride on this wave of internet. So let us go now a little bit deep into the IoT and look at the IoT platform. So this is a typical IoT platform. So whenever we talk about IoT, we talk about a device, but that device has different layers, different platforms. One of the layers is the user layer or the environment layer, where that IoT device is either communicating with the environment or it is communicating with the user. Just below that, we have the things in internet. For example, we have sensors and actuators and some communication things. Then we have another layer of communications network layer, which is connected to the internet via some gateway. And then that internet actually connects us to the server. And then based upon like which server we are picking, based upon where we are transmitting the data, we have fog IoT, we have some kind of edge IoT devices as well. And we might actually briefly discuss edge IoT and fog IoT in next sessions. So say, for example, I have XM1000. It has got two sensors. It has got some communications, RF communication system. Then that device is connected to the internet, so that this XM1000 is the IoT device capable of actually communicating with the internet. In today's class, in today's session, we are discussing on to this layer, which is the device level layer. We are just talking about the things, especially we are talking about the sensors and actuators. So let us define a sensor. So in layman's term, sensor converts a non-electrical input into an electrical signal that can be sent to an electronic circuit. There is more formal definition by IEEE, which says that an electronic device that produces electrical, optical, or digital data derived from the physical condition or event. So, electronic device which produces electrical, optical, and digital data, which has been derived from physical condition, is a sensor. Now, it also adds that the data produced from the sensors is then electronically transmitted by another device into information that is useful in decision making by some intelligent devices. And that is actually the realm of actually IoT. So here we are actually talking about IoT, and here we're talking about sensor. So here we're talking about the electronic device that is actually producing electrical, optical, or digital data from the different physical conditions or for different events. So what we'll do is like we'll just look into the actual sensors and try to actually compare that with the human body. So this is one of the examples I like. So we have 5 sensors. We have vision, smell, touch, all these sensors are there. So we use these sensors to get the data. That data is processed in our brain, and then that data is transmitted, the processed data is transmitted to our limbs so as to take some kind of action. If I can just compare that with the IoT device, then we have sensors which are actually trying to convert the physical phenomena into electrical signal. That electrical signal is being processed in the CPU, and the process information is being fed to the actuators to perform certain actions. Now, then is that so that like the sensors and actuators are the same thing? The answer is no. The sensors are different and actuators are different. Essentially, when we talk about sensors, sensors actually sense certain things and measure certain things from the real world. So we have a physical environment, we have a real world. Sensors actually sense that physical environment, measure certain quantities, measure certain parameters, and send that to the next device in the form of electrical signal. Whereas actuators do the exact opposite thing. They take electrical signal. Based on that electrical signal, they act and do some useful work, and that useful work is done in the real world or physical environment. And just to actually see like what is the difference between sensors and actuators, we have a really nice example of lever control system. Say, for example, we have a level control system in our house. What we're doing here is we are actually trying to process the information and act on that processed information. So right now, in this example, we have two sensors. We have a sight tube and we have an optical nerve, which is actually trying to sense the level of this water. Then that data is being sent to the processor, which is our brain. And then our brain is actually giving signals to our hand, which is actuator, to close or open the wall. Okay, so this is something, we're processing something, and then we're actually acting upon it. Another example, very good example in our computer system is the temperature controller. Say, for example, we have a thermocouple here, which is sensing temperature of CPU. If the temperature falls below or actually goes above certain range, then actually microprocessor gives some command to control the speed of the fan to keep the temperature constant. So we have a sensor over here and we have the actuator over here, which acts on the directions of the microprocessor. Now I'm going to introduce one more concept of transducers, and then we'll see what is the exact difference between sensors, actuators, and transducers. Okay, so let us define transducer. Now, transducer converts a stimulus from one signal domain to another signal domain. Now, what are those different signal domains? A stimulus can be mechanical stimulus, it can be magnetic stimulus, it can be chemical, it can be thermal stimulus. That stimulus in that domain, in chemical domain or mechanical or radiant domain, is converted by transducer to the another signal domain, for example, mechanical or thermal. Now, what sensor does is, sensors actually receive stimulus in one of the domains, for example, chemical or magnetic, and then convert it into electrical signal. So sensors convert stimulus and respond with an electrical signal, whereas actuators convert electrical signal to another signal domain. So essentially, sensors and actuators are the subsets of transducers, which convert stimulus from one signal domain to the another signal domain. So we have a small example over here. In this example, what we're going to see is a microphone and a loudspeaker. So at the microphone, we are converting sound, which is mechanical signal, into electrical signal. And then that electrical signal at the loudspeaker is getting converted to again mechanical signal. So in this portion, towards the mic, we have sensor, and onto the loudspeaker side, we have actuator. So that is the difference between sensors and actuators. Many times students and of course the people working in IoT domain get confused between transducers, sensors and domains, sensors and actuators. So just remember that transducers is a broader term. Sensors and actuators are subsets of transducers. We are going to focus in today's lecture on sensors, which means we're actually trying to convert any physical stimulus or any stimulus to the electrical signal. So let us look at some different types of sensors, and then we will actually go with the advanced sensors. Now, there are different types of sensors available, and they are classified based on what they do, how they do, where they do. The first type of sensors or the first type of classification is active or passive. If the sensors produce an energy output or require an external power supply, we call them as active sensors. If the sensors doesn't require any external power supply, then they are passive sensors. Then there are some different types of sensors which are known as contact or non-contact sensor based on whether they are actually making any physical contact or not. The best example is temperature sensor. We have some temperature sensor which are contact sensors and some of them are non-contact sensors. Then we have absolute or relative sensors. Absolute sensors measure the absolute scale. But if the sensor is actually measuring something based on the difference between fixed and variable reference, then it is relative sensor. Now, we also often classify sensors based on how sensors measure different things or what mechanism they use to measure some physical quantity. For example, thermoelectric sensors, electrochemical sensors, piezoresistive sensors. So those sensors are classified based on how the sensing mechanism works. And then at the end, which is most commonly used technique, is what sensors measure. Sensors can be categorized based on their applications or what physical variables they measure. And the last type of sensor classification is widely used. So what sensor measures is more important. If they're measuring temperature, then it is temperature sensor. For humidity, it is humidity sensor. We have different sensors for different applications. We have sound sensor, acoustic sensors. We have IR sensors. So sensors are categorized based on their application or what physical variables they measure. I have a list of sensors, of course, borrowed from internet. uh, so we have position sensors. The best example is potentiometer, proximity sensor. Then we have occupation or motion sensor. The best example is radar. We have velocity and acceleration sensor. Example is gyroscope or accelerometer in your cell phone. We have force sensor. We have pressure sensor. We also have some flow sensors. For example, anemometer. We have acoustic sensors, humidity, light, radiation sensor. Radiation sensor example is Geiger-Müller counter or scintillator detectors. We have temperature sensors. We have chemical sensors and biosensors. My research domain is into chemical sensors and biosensors. So I work in this domain, of course, but I make use of all the different types of sensors as well. Now, your cell phone is the best example of nicely packaged sensor for different applications. So if I actually look into your cell phone has proximity sensor, it has magnetometer, accelerometer, humidity sensor. In some of the cell phones, we have gyroscope, we have camera, pedometer, we have light sensor, thermometer, we have fingerprint sensor nowadays. So all these things are actually packed nicely in our cell phone. And many times, like when I start actually teaching with the sensors course, I ask my students to actually just open the cell phone, play with it, and to try to just separate all the sensors and see how, where they are located, how they are located, what is their size and everything. Okay, so now let us look at some of the commonly used IoT sensors. Okay, before that, do you have any questions or do you have any concerns? Am I properly audible?
Yes, sir, you're audible.
Yeah, perfect. Yeah, thank you. Dr. Bhardwaj is asking, like, could you please share the slide with us? Yes, I'll share the slides with you. I'll actually send it to Dr. Pushpa, and then he will actually share it with you. Yeah, perfect. Yeah, so Dr. Satish is saying like some sensors are related to agriculture. Yeah, and actually, I'll actually mention briefly about the agriculture sensor as well when we take the examples. Perfect. Okay, so let us look at some of the commonly used IoT sensors. I have picked these sensors because they are readily available in the market. The price is very less, maybe for 1 rupee or for 5 rupee or for 10 rupee, we can now get these IoT sensors, and they're quite useful. They're very important in finding out different physical parameters. And the very first example is temperature sensor, which you get it for a couple of rupees. Now, what is this temperature sensor? Of course, to measure temperature using the principle of thermocouple, which consists of two dissimilar conductors. Uh, and we also use some kind of RTTs, resistance temperature detectors, to measure temperature. Some of the common RTTs are platinum, which is very popular and quite accurate. We can use nickel, we can use copper. Sometimes we do use aluminum and tungsten as well. Of course, tungsten is expensive, but it is still very useful. So these are the RTTs used for temperature detection. Nowadays, the temperature sensor, which you can buy from any shop or from Amazon, is very easy. I mean, it is very easily available. It is very cheap. For almost a couple of rupees, you can get this sensor. The next sensor, which is a little bit expensive, but it is very useful, is proximity sensor. It is used to detect the motion. It essentially consists of some kind of circuit to emit the electromagnetic field or a beam of electromagnetic radiation to look for the changes in the field or return signal. Now, depending upon what type of material you are trying to detect, there can be different types of proximity sensors. We can use capacitive sensor or photoelectric sensor for plastic targets, and we can use inductive sensor for metal target. We also have some pressure sensors available, and we might actually go a little bit deeper into that. So the pressure sensor is equipped with some kind of pressure sensitive material, which is used to measure the pressure of liquid or gas or any fluid uh, against a diaphragm made up of either silicon or stainless steel. We also make use of some of the materials such as quartz to see what is the pressure. One of the examples is given in the next slide. We use piezoelectric pressure sensors. So some of the crystals have tendency that when we actually press them, or like when we apply some kind of pressure, they get elastically deformed. And when they actually deform, they actually undergo some kind of electrical changes. When the crystal is deformed, the electric charge is generated for only few seconds, and then that charge can be actually counted towards finding out like what is the pressure which we have applied. Most commonly we use quartz because it is readily available, it is very inexpensive. But in some of the applications, we also use tourmaline. It is the alternative which gives much faster response, typically in the order of microseconds. And we use these kind of pressure sensors for some of the defense applications where we really need to select what is actually happening under the water. And for that, instead of using quartz, we use this tourmaline. Now, the next kind of pressure sensor is based on silicon. It is based on the piezoresistive properties of silicon. What essentially we have in this kind of sensor is a thin diaphragm. So when pressure is actually imposed, or when it is pressurized, there is slight change into this silicon diaphragm, change in shape, which gives rise to change in resistance. And that actually diaphragm is connected to a Wheatstone's bridge, which actually shows what is the change in resistance, which essentially is counted towards the change in pressure. There is another type of pressure sensor. We call it as capacitance pressure sensor. It is very simple to use and simple to fabricate. What we essentially have is a etched silicon diaphragm, which is over here. It is essentially based on the earlier principle. And when we apply pressure, there is a change in diaphragm. Now, we also have some kind of high frequency oscillator which is connected to this diaphragm. So based on the change in the shape of this diaphragm, we get the output which is counted towards the change in pressure. This kind of pressure, capacitive pressure sensor, is again used for oceanic sensing applications used by Navy, and they are also commonly used in big tanks or big vessels to measure the pressure. Next kind of sensor, which is again readily available, which is very often used, is IR sensor. It is used to detect the infrared lights. They are used to visualize heat leaks in houses. They're also used to identify environmental chemicals and radiation hazards. And they can also be used to measure blood flow in hospitals. And the good thing about these IR sensors is nowadays they are often integrated with the wearable sensors in wearable devices such as Fitbit, Apple Watch, and Samsung Gear. The next kind of sensor which our kids use most is ultrasonic sensor. Many times, nowadays kids are using these robots, and all those robots do come with this ultrasonic sensor. So it is used to measure the distance between two objects by using sound waves. You know the principle of radar. So it is based on the same principle. It measures the distance by sending sound waves at a specific frequency and then listen that sound and thereby to measure the distance. Now there are two types of ultrasonic sensors. This first type is active sensor. The another one is passive, of course. The active sensor generate high frequency sound, and then they also receive back the ultrasonic sensor for evaluating the echo. Whereas passive ultrasonic sensors, they don't emit signal, but they just actually absorb the signal or detect the ultrasonic noise in the specific conditions. Now, the next kind of sensor where a lot of research is happening, I can see like there are some people from Pune University. So there is a very active group, applied physics group in Pune University. They work in gas sensors. So we are using gas sensors to detect some specific target gases such as carbon monoxide, hydrogen, ammonia, ozone, propane, butane. Recently, there have been some advances into two sensors. There are some advances in N2O sensors to look at different gases and like how we can actually just quantify them properly, accurately. One of the common applications is smoke detector, where we use this gas sensor to indicate, to detect smoke and thereby detecting the fire. I guess like I received one. Okay, there is one question by T. Nazia. Pressure sensor is a load sensor. Yes, it can be a load sensor. I did not take that particular example, but it can be a load sensor as well. And then there can be some kind of torsional sensors as well. There are some kind of force sensors as well, which can be used for sensing the actual load. Okay, let me go back. Okay, and now one of the sensors which I just talked about earlier, and one of your colleagues actually asked about, is the water quality sensor. Now, there are a bunch of water quality sensors available in market, and they're actually easily available. One of the best examples is of pH sensor. pH sensor can be active sensor or can be passive sensor. We have some sensors to measure salinity of the water, to measure the conductivity of water, to measure the presence of pesticides. And then there is new kind of sensors which are evolving, and which are coming to market, and those are NPK sensors. So these NPK sensors are used for agriculture sensor to detect what is the level of phosphate, what is the level of different minerals into the soil, and for that application. Essentially, what they are doing is these NPK sensors or some types of sensors are chemical sensors, and there is new company in Pune which are actually working on this NPK sensor to create some kind of smart agricultural platform. So what they're doing is they're trying to measure the moisture, pH, along with NPK values in the soil, and thereby feeding the proper amount of NPK for the plant growth. So those kind of activities are happening right in Pune. Of course, like there are some companies in, I know some of the companies in Indore as well who are working into the NPK sensors. There is one company in Bangalore as well who are working into that area. So the NPK sensor business is now growing very rapidly, and most of the farmers are now getting aware of these sensors and they are using it into their farms. Okay, so all these sensors which I mentioned so far are kind of commercially available sensors uh, or readily available sensors which you can go to market and buy it. In the next segment, I'm going to talk about some of the advanced sensors which are used for specific applications, and I'm going to talk about some of the research which is happening into that area, and most of the research which is from my lab as well. Okay, so let us go to advanced sensor, and then let us look at one of these images. I like this image because it is one of the first functional device which was reported almost now 20 years ago by India National Laboratory. So it is essentially a torsional ratcheting actuator. So it is an actuator which is actually moving in one direction, and then there are some kind of ratchets so that the opposite motion is restricted. And this is some kind of device which was actually fabricated on the scale of almost few hundred micrometers. So you can see here this length is about 100 micrometers. So the entire thing was about 500 micrometers. We tried to replicate some of these things in our lab, and we are also actually pioneers in actually making some of the MEMS devices for different applications. One of the applications which I'm going to talk about is a micro mirror array for optical microspectrometer. Now, many times, like whenever we actually talk about communication, we just talk about electrical communication, and we forget about optical communication. But that is the area which is growing very rapidly, and with the advent of quantum technologies now, optical communication will be actually on the top of everything. So we actually wanted to actually dive into some of the optical phenomena. So we thought of actually fabricating a microspectrometer. It was optical microphotometer, a microspectrophotometer. So this optical microspectrometer is tunable for optical detection of multiple wavelengths. So we can detect multiple wavelengths using this microspectrometer. It essentially consists of few mirrors which we can reposition, and we can actually just change their position and thereby reflect the light in one particular angle. And by doing so, we can actually selectively choose the wavelength for different chemical as well as biological detection by absorption. The design is very simple. What we have here is a hinge on, and we have actually some kind of rotatory movement, and we have a hinge over here, and we can actually move this mirror. This is the mirror by giving some kind of signal so that we can actually properly align our mirror. The entire length here is about 500 micrometers, and the size of the hinge is about 200 micrometers. Uh, Here is the uh, diagram, the elaborated diagram. We have a axle over here. We have a hinge lock over here. We have a rotatory disc over here, and we have mirror and some kind of release holes over here. And this is the actual device which you can see. It's a MEMS device, so we can actually just move this this actually rotor by using some kind of mechanism along the hinge. So quite nice device, and we can actually align many things by just controlling this rotatory motion, and that application is quite successful. Now, based on the same principle, what we did is we created some kind of micro corner cube reflectometer. So what we did is we actually fabricated CCR. CCR means corner cube reflectometer. It is actually made up of 3 different reflective surfaces or mirrors. And by changing the angle between these 3 mirrors, we can actually reflect the signal to the detector, which is positioned right towards the source. So source and detectors are close to each other. By adjusting these mirrors, we can actually send back this signal to the detector, which is very close to the source. And this is the actual MEMS device. We use micro electromechanical system, where we use nanofabrication. We use fabrication processes to etch the silicon. Silicon was properly etched at different angles, and we created this kind of CCR or corner cube reflectometer. This is one of the images, SM images, and this is the size of this device. So this is a quarter, and on the quarter we have a device which is almost about 8 millimeters by 8 millimeters. So these things can happen with the help of these micro electromechanical systems. Now, as things are progressing, as the research is progressing in this area, we are now generating or creating or producing different types of sensors which are based on MEMs or micro electromechanical systems. There is some advances in fabrication. There are some advances in silicon technologies, and with the advances in silicon technologies and with the advances in fabrication technologies, we can actually create some different types of sensors. And one of the sensors which we created was for ocean sensor. And that sensor, I'm just actually going to show it for you over here. So we actually use that sensor, which was pressure sensor, which was created using MEMS technology, was used to find the dynamics of ocean sensing. So for example, we have a boat over here, we have a ship, and we have some disturbance deep down the surface. And there is some kind of process happening over here. So it is some kind of biological process. So there might be some kind of fishes, there might be some kind of shells lying around, there might be some kind of corals, and there might be some kind of physical process as well happening over here. So maybe one of the submarines is actually going from here. So based on the principle of capacitive sensors, we actually studied the dynamics of ocean sensing. And these are different graphs. I'm not actually going to go much deeper into that, but it was one of the examples where micro electromechanical systems was used to detect different types of signals. So those were actual sensors used to find what is happening underneath the water. And that we almost did 10 years ago. And since then, we have actually progressed a lot. And I couldn't actually include those slides, but nowadays what we are using is we're actually trying to apply AI and machine learning techniques to find out what is the speed and what is the wake field and what is the actually size of the ship and everything. All those things we are able to find using these kind of small sensors, which are fabricated using MEMS technology. But we are nowadays actually going more and more into different sensors. We are slightly shifted from these ocean sensors, and now we are using MEMS technology for wearable sensors. Now this wearable sensor business is growing like anything. And IoT and IoT, Internet of Medical Things, is actually fueling the advances in wearable sensors. And perhaps like advances in wearable sensors is fueling the advances in IoT and IoT devices. Now, what exactly we do or when we actually talk about wearable sensors? Let us look at this subject, a person walking. So the person is in motion. So say, for example, we have three different sensors. The first sensor is measuring the heart rate and respiratory rate. The other sensor is measuring the motion. The third, again, is a motion sensor. All that data is being collected through some aggregator, and that data is being fed to the internet, where we have some kind of machine learning algorithms or some kind of data analytical softwares are present over there. Some analytics is happening over there, and then that data is being fed to the emergency services, to the family members, and to clinicians. And based on the data received from your body, from subject's body, your family members, emergency services, and doctors are intervening and actually taking some kind of action so as to reach closer to you. I often actually show this image, which is quite interesting image, and where actually number of wearable devices is increasing like anything. We have almost 10 or 12 different big players into the market. The major ones are, of course, Apple, Samsung. We have now some of the watch manufacturers which are coming into it. Recently, we had a Tissot watch, smartwatch. We have Fossil smartwatch. All those actually watches and all those sensors are trying to actually find different physiological parameters on your body. Recently, Apple has launched a new sensor where it can measure the EKG or ECG using Apple Watch. Along with that, they can also measure heart rate, they can measure the blood flow rate, they can of course measure number of steps taken by you, and all that data is collectively being taken, collectively being processed, and then actually being sent to the cloud or to the aggregator. What we are interested in is to find out some of the biological parameters or biological markers using these wearable sensors. And that's why in our lab right now, we are working on three different types of wearable sensors. The first type of sensor is alcohol sensor. So we can use this type of sensor to measure what is the level of alcohol in your body. Another type of sensor which we are working on is wound sensor. If we have any chronic wound, or if there is any kind of skin disorder, we can actually measure or we can monitor the wound healing process or the disease of your skin by using our sensor. And the third sensor, which I might elaborate a little more, is a stress sensor. It is used to quantify this sensor, or sorry, quantify the stress in human subjects, and thereby we can actually see how much help that person needs for the next activities. So we'll start, or we will go one by one and look at different types of sensors which we are using. And then at the end, we'll combine all these sensors and we'll look at them as a IoT or IoT device. Okay, so let us go ahead and look at one of the sensors. Sorry, I just wait for a minute. There is some disturbance. Okay, sorry for this disturbance. Okay, so as I mentioned, we'll look at three different types of sensors, which are biological sensors, and how they can be used as IoT device and IoT device. Now, this is the wearable device which we have fabricated in our lab. That device essentially consists of a micro fuel cell sensor, uh, and it also consists of some kind of flexible electronics. We have essentially a potentiostat and a controller and one communicator, and its size is typically about 2.5 centimeters, less than 2.5 centimeters, about an inch. This much big, yeah, and amount of acetone coming out from your body. And based on the amount of acetone coming from your body, it actually changes its properties. Essentially, it changes its resistance and it changes its. This kind of sensor is used to measure the blood alcohol content. So what happens is whenever a person consumes some alcohol, uh, the alcohol content in blood increases linearly. So the blue dots which you may be able to see, these are the theoretical points where like we can actually have a blood alcohol content after the consumption of alcohol. So at t is equal to 0, we have consumed alcohol, and after almost 30 minutes, we can see that there is a rise in a blood alcohol content, which is linear rise. So what happens is, uh, if we use a normal breath analyzer, which law enforcement people use, they kind of get false readings in initial phases. For example, here, immediately after consuming alcohol, within 30 to 60 minutes, they get very high level of alcohol content from your breath. And after certain time, which is almost about 88 minutes or about 90 minutes, there is sharp decline in the uh, in the alcohol content in your breath. So it kind of gives some kind of false indication. Whereas the alcohol sensor which we have developed has some kind of near actually linear rise in initial phases. Then there is some sudden jump which we are working on right now, and then it again rises linearly, and then there is some kind of exponential fall which is better than the breath analyzer. Now we have been actually talking to the Miami-Dade Police County Police Department, Miami-Dade County Police Department, to use these variable alcohol monitor sensors to find what is the blood level, or sorry, blood alcohol level in some of the drivers. For example, what we are imagining is that if a person has actually consumed alcohol, our wearable device will be able to monitor the blood alcohol content in person's body. It will communicate that blood alcohol content to the family members. If it is beyond certain limit, then it might be actually sent to some law enforcement people as well as to some of the other aggregators where they will be able to take proper action. However, we had some kind of setbacks and we couldn't do it. Of course, like we are still in talks with the police departments and everything. But recently, what we have done is like we have slightly converted this wearable device into the anesthesia measurement device. Now, what happens is like in many cases, when you're going through some kind of surgery or some procedure, uh, we actually use anesthesia and we rely on patient's response or subject's response to that anesthesia. So like doctors just ask like to count 1, 2, 3, 4, 5, 6, and about 6 or 7, at 6 or 7, you actually just lose your senses or you lose your conscious. And afterwards, actually, medical practitioners actually start doing surgery and everything. What we have found is that like the variable monitor device which I'm presenting here is capable of finding the level of anesthesia in your body based on the same principle as that of the IoT sensor. And that can be used for accurately the amount of dose given to the patient for the purpose of anesthesia. And the clinical trials are under progress, and they actually were now essentially kind of IoT device, but it is more like a sensor. But I wanted to actually just mention it to you now here is the wearable wound biosensor. Now, what is this wearable wound biosensor? Many times, like you might have seen that if we have any wound on a skin, and if it is chronic wound, for example, in case of diabetes, if the wound is chronic, it is very much difficult to see how the healing is happening, how the healing is processing. If you want to see like the healing process, what you have to do is like you have to remove the gauze or you have to remove the bandage and then see like what is happening inside. What we are proposing, and there are multiple groups working on this project all over the world, is to embed some kind of sensors into the dressing itself. So right now we're actually researching on, maybe I can go to the next slide, chemical sensor or chemical sensor, biochemical sensors onto the dressing or onto the gauze. We have the array of these biological sensors, and this area will be the wound area. And what we'll do is like we'll measure the uric acid level into the wound area. Now, uric acid is the indicator of the wound monitoring process. Lesser is the uric acid, better is the wound healing process. So thereby just measuring the uric acid level, we can actually measure the wound healing process. And we have actually converted that, and just forget about this one. We have some kind of more advances into it. Maybe I can go to the next slide. So we have made some kind of flexible electronics. We have flexible gauge where the biosensors are fabricated. We have flexible electronics on Capton, and then that has been integrated into the gauge or into the dressing, and thereby we can see what is the level of uric acid. We are now also trying to incorporate, we are also trying to integrate pH sensor, temperature sensor, and humidity sensor into the dressing itself, so that we can get the complete information about the wound environment. Now, one of the other things what we are trying to do is, since like there is active communication happening between the with the sensor and the aggregator, there is loss of power. So we are actually trying to work on the wireless power transmission for this kind of dressing. So essentially, whenever we're talking about smart dressing, it is not the biological problem or it is not a medical problem, but it is essentially electrical and communications problem. We are working on sensors, we are working on communication, we are working on wireless power transmission, and we are working with AI and machine learning to see how the wound is healing. And that all things form the IoT ecosystem. The IoT made up of some kind of communication devices, data aggregation, data processing, and making some kind of. Now, we're going to go to the next application, and then I will stop and then I'll take your questions. The last example here is cortisol biosensor for monitoring stress. Now, many times we often use word that I'm very much stressed because I had to do this, I had to do that. I was busy whole day. I worked a lot and that's why I'm stressed. but we never quantify stress. We never say that I'm 50% stressed, I'm 100% stressed, I'm 80% stressed. So we are actually working on stress sensor which can quantify the stress level in human subject. And for that, we are using a biomarker called cortisol. Now that cortisol biomarker is present in your body fluids, it is present in your blood, it is present in your saliva, it is present in sweat. Many a times, if you are too much stressed, it is present in your hair, in your nails as well. What we're doing is we are measuring cortisol biomarker in your saliva and in your sweat. And that's why like, we have created some kind of sweat patches, which will be actually placed just underneath your wearable device. For example, if you are using Apple Watch or for example, Samsung Gear, or even your normal watch, you can see that there is some kind of sweat which is attached to your watch surface. We are actually trying to collect that sweat and try to find what is the cortisol level into that sweat using our biosensing technology. Now, where we are applying this technique, we are actually talking to the Department of Defense, and we are actually communicating with them to measure the stress in drone pilots. We are also talking to some of the athlete groups and teams. For example, we are talking to Florida Panther team for measuring the stress in their players. So, for example, if there is a training session happening, and if the person or if the player is very much stressed, then we can change the routine of that person's training by measuring the stress into that uh, into that particular athlete. So these are some kind of use cases, but our focus is mainly on developing a stress sensor. So that stress sensor is actually based on biochemical sensing. We have a stress marker called cortisol. If the cortisol gets connected to some of the elements such as graphene or some kind of nanoparticles, we see the change in impedance. We measure that impedance, and based on that impedance, change in impedance, we find what is the level of cortisol. And earlier processes were very tedious. We used to use some kind of electrochemistry for that, but we recently changed that process, and now we are using extended gate field effect transistor to measure the direct readout from the direct readout of cortisol level using this effect technology. What essentially we do is like we put some kind of saliva over here, we apply some kind of voltage, which is actually gate voltage. Based on the cortisol level, there is some change in impedance, which gives rise to some change in input gate voltage, which is actually in turn affects the IV characteristics of your FET field effect transistor, and that is actually correlated with the stress level. Going one step further, what we are also trying to do is to look at the facial expressions of our athletes and trying to correlate the facial expressions of our athletes with the stress. And we're actually trying to do some kind of develop some kind of deep learning modules so that by just looking at the facial expressions, we will be able to quantify the human stress uh, and thereby actually make some kind of measurements or make some kind of actually next actions. So again, essentially here it is a complete IoT package where we are using biosensors to measure cortisol in a human subject. We are using facial expressions to look at different actually stress indications. We are using AI to make some kind of decisions, and then we're actually just giving some kind of feedback to the person in real time. And that is essentially is IoT. Now, but if you want to do this kind of IoT, we just cannot rely on sensors. We also have to have some kind of active smart object. And I just actually go to the uh, entire slide. So the real power of these smart objects or sensors come from being networked together rather than just being isolated or standalone objects. And whenever we talk about smart objects, we just don't talk about one particular sensor, but we talk about the entire device, which has minimum of four characteristics. The first one is processing unit, where the entire process is taking place. Then, of course, we have sensors and or actuators. We should have a communication device and we have a power source. And this entire package is a smart object, which is a building block of IoT. So I might be taking one more session with you. And during that session, I'm going to talk more about like how we can use data from these sensors and how we can actually properly visualize to make some sense out of it. Okay, so just before I close everything, I would like to show you one of the uh, videos by my students. They are working on variable cortisol sensor. They made just a small movie last year, and I like that movie, so I keep on actually showing it to everyone. So let me actually just see if I can run it here. No. Okay, so let me actually just go to here. Yes, now it's working. Am I audible? Because I just received one message that there was no sound. Can you hear me?
Yes, sir, we can hear you. The only problem was the YouTube voice is not there.
Okay,
It's
perfect.
no.
Okay, no worries. Anyway, like I'll be sharing my slides so that you can actually just go through all these videos and all this material. So that should not be a problem. Yeah. Okay. So I can see that like there are a lot of questions. Let me just finish my slides and then I can actually go back to my get back to your questions. Okay. Now, what is happening in recent years is that the sensors are getting better, and because the very first thing is their size is decreasing. We are extensively using MEMS technology for miniaturizing these sensors. The perfect example is the temperature sensor. Earlier, the temperature sensor was very bulky. Nowadays, the temperature sensor can come into the size of about few microns as well. So the size of the smart objects is decreasing. The next thing what is happening is that as size is decreasing, the power consumption is also decreasing. And with that, there is also rise in processing power increase, which is of course, which is correlated. We are actually trying to improve the communication capabilities. We are also trying to standardize the communication uh, processes. And that's why now is the time to work into IoT and make use of this IoT for different applications. So I hope, I mean, like, you will learn a lot of things about IoT in this faculty development program, and maybe actually disseminate that knowledge to your students, and maybe you can use that knowledge in your own research. So if you have any questions, do let me know here. I'll be going to your question one by one, and then I'll actually just answer them. Okay. Now, there is one question which I did not respond, is metal detector sensor question mark. I'm not sure like what that question is about. If you could write it one more time, then I can actually elaborate that. Then there is one more question. Sir, for pH measurement, electrode and sensor are same. No, actually it depends upon what kind of pH measurement you are doing. Many times the electrode and sensor are same because electrode itself is a sensor. So that's why it is same. But for example, litmus paper. Litmus paper is also a sensor. So there is no electrode. So there are a bunch of sensors which are not essentially be the same as electrode, and we can have a different sensing material, and that sensing material may be connected to an electrode through some connections. Okay. Then this question I did not actually understand. How can we calculate traffic changes in IoT? Okay. I did not actually get this question. Maybe if you could elaborate that, I'll answer it. Then MQ3 alcohol sensor, I did not. Maybe like these questions were there when I was talking, I couldn't see those questions. Okay. Now another question is there, like how these variable sensor data is secure. Okay. Now there is a lot of work going on in security of sensor data. There are two new technologies which we are using. One of the technologies is cryptography, which is obvious. So everything is encrypted. So only the end user and the person who requested their data will have access to it. Another thing which we are actually trying to implement, and one of few of the students from IIT Pune are working on it, is they are using blockchain technology to secure this data. So there are new advances happening, but very first thing is like the encryption is the key for all these data transfer. Okay, your voice is breaking. Okay, there's one more question. Is there any sensor for fatigue measurement? Maybe we can relate fatigue with the stress, and if we could actually relate fatigue with stress, then we can actually measure the stress. So I believe we can actually measure fatigue using our sensor. But as such, as far as I'm concerned, I'm not aware of any sensor which actually is trying to measure fatigue in human subject. Okay. Okay. Is there any sensor for eye parameter measurement for eye diseases? Okay. There are no sensors available for eye measurements, but one of my colleagues is actually working on actually image processing. So what they are doing is they are actually trying to take different images of eye. They're actually imaging them properly and using some kind of data analytics. They're actually trying to correlate that with the blood sugar. They're also trying to correlate that with your bodily parameters, and thereby actually they can actually talk about some of the aspects about glaucoma and related things. But there is no sensor as such. But by just looking at, maybe we can just use a camera, optical sensor. We can use a camera to image your eye and then actually correlate some of the parameters with your physiological parameters. Okay, there is one more question. Which sensor to use for gas leakage detection? What distance you have to keep? Now, typically, it is advisable that you have to actually use a specific sensor for specific gas. For example, I have mentioned in my slides, there are different types of sensors like CO sensor, hydrogen sensor, ammonia sensor. We have some kind of N2O sensors as well. Those sensors, a typical distance between your event and sensor for a room, I guess, I mean, you are asking about a room, is typically about 5 feet or so. So whenever you are placing your sensor uh, in your room, make sure that like it is at the center of the room, just below the fan or somewhere, so that you can actually cover everything. I mean, it is all about coming into the circle, falling into the circle. So choose that distance. Okay. Okay, there is one good question is it essential to use AI between AI and IoT? Okay, and my answer is yes and no. Because as I mentioned, whenever we talk about IoT, we talk about getting some data from a sensor and processing it. And whenever, if we're just processing one type of data, for example, I have a camera which is actually taking pictures, and I'm just concerned about the quality of the pictures, then I don't require any other type of data. And in that case, I may not use AI. But whenever we talk about IoT ecosystem, we don't just rely on one particular data. We try to take as much as data as possible. For example, if I'm in a factory and I'm producing, say, for example, a juice. So if I'm producing a juice, then maybe apple juice or maybe mango juice, then what I have to look at is the color of my mango juice, the taste of my mango juice, the temperature at which it was stored, the temperature at which it was processed. So I have to actually look at 3 or 4 or 5 different parameters, and then I have to actually make sense using those 3 or 4 or 5 parameters to find whether my juice has particular taste or not. And there AI comes into picture. So you may use AI, you may not use AI, but if you really want to use IoT, then you should be combining AI so that you can get more value from your data. Okay. There is another question which is quite interesting. I had actually thought of discussing it, which is what is current research going on Internet of Vehicles or vehicles connected using IoT? Now, I definitely know 3 different companies which are working into Internet of Vehicles. One of the companies is Tesla. You all have heard about it. They are actually working on self-driving cars. What they are doing is they are actually are putting different types of sensors. There are visual sensors. There are some kind of pressure sensors, temperature sensors. There are some kind of proximity sensors. They are putting all these sensors onto vehicle. These sensors are actually looking at the external parameters, external environment, as well as they are monitoring your vehicle. Okay, what is the load in the vehicle, what is the wear and tear of your vehicle, what is the tire pressure and everything, and then they're trying to make a sense out of it. So Tesla is definitely working on it for self-driving vehicles. Another company which is extensively investing is Uber. Uber is trying to get rid of their drivers, and they want to establish autopilot cars. At least in California, they want to do that. There might be little difficulties in implementing them in other parts of United States of America, or perhaps in Europe or in India or China. And one of the actually Uber employees, when they were talking to us in one of the conferences, they mentioned that if we could drive our car in Mumbai, then we can drive our car everywhere else. But that might happen in within 5 years. It may not happen immediately. But of course, in California, they are actually trying to implement that next year. So Uber is there. And then there is another company which is extensively working into this area is Google. You might have heard of Google's self-driving cars, and they're also doing very good research into that area. One of the other research which is happening related to Internet of Vehicles or vehicles connected to IoT is the collision damage systems, where all the cars are connected to each other. They are trying to communicate with each other, and thereby we're trying to reduce the collisions at the internet intersections. So if we have some kind of obstacles at the intersection, all the cars may stop or they'll take actions depending upon the other car's response. Okay. Okay, now there is one more question. How can we choose a sensor for particular application? Uh, it depends upon what you want to measure. For example, uh, we had the similar problem earlier. One of my colleagues is working on finding the N2O level in the Miami-Dade region, and typical N2O uh, 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 level is about in micrograms, basically micrograms per liter. And the sensors which that person is actually working on did not have that kind of sensitivity. So they had to actually work on the sensitivity and then use that sensor for that application. So like whenever we have a sensor, we look for the sensitivity of the sensor. We look for the selectivity of the sensor. We also look for the operationability of that sensor. For example, is it easy to operate in that particular environment? Can we place that sensor in that particular environment? So all these things come into picture when you have to choose a particular sensor. Okay, this is good question, and like I was expecting this question. So what type of lab infra needed to do projects and research for both students and faculty? Okay, now I might actually share some of the pictures from our IoT labs, but essentially, and I was talking to Dr. Kushwa as well last week, is that all the IoT labs can be done using just one Arduino Uno or Raspberry Pi. If you have access to Raspberry Pi, if you have access to laptop, then you can do everything, or you can actually use those things to teach IoT to your students. In our lab, if you go to our lab, what we have is like we have a bunch of IoT Arduino Uno boards. We have Raspberry Pi. We have a bunch of sensors lying here and there. We have typical electronics lab where actually student can actually solder different sensors and everything onto board and everything. And we also have some of the, we also have some sensors and we have some kind of cloud, internal cloud. But internal cloud is not required for that. You can make use of Microsoft Azure, which is free to use. You can also use AWS IoT. You can also actually look for some of the IoT platforms which are free to use. And I'll be talking to you about one of the free platforms, which is ThingsBoard, in my next session. And so you need not have to actually invest much money into that. Okay, there is one more question is, what range a chemical or biological sensor sense? Okay, I gave you two examples or three examples rather. The first example was cortisol. Our sensors can actually sense the picomolar of substance in a liter. So we can actually sense picomolar, and we can go up to millimolar range with the existing biochemical sensors in our lab. But then there are some kind of sensors which can actually go up to few tens of millimolar size, which is the limit. So we can essentially go from some millimolar, drop down to some few picomolars. Okay, sir, can we reach out to you in future if we need to help in our research work? Yes, you can reach out to me. I'm just going to put my email address over here. You can just send an email. It's mmujawar@fiu.edu. Just send me an email and then I'll respond to your email. Okay. Can you suggest a company which can supply good sensors? I'll actually send you a list of companies from where we order our supplies. I don't have it on top of my head now, but I can actually send that to you maybe by next session. Okay. Any other question?
Think we have already gone through the many questions. So thank you, sir, for very informative lecture.
Okay, yeah, thank you.
And definitely we are going to have two more sessions from sir. So if you have any more question, you can email to sir.
Yeah, okay. Thank you very
everyone.
much.
Thank you, sir.
Bye. Take care.
So, okay, we will meet tomorrow at 10 a.m. Okay, thank you, everyone. And the tomorrow link will be shared on your email.
Hello. Hello, am I audible?
Yes, ma'am, you are audible, very much
Yes.
audible. Please tell me.
Okay. Actually, I would like to know regarding this session attendance, how we can give the attendance, because in our mail we don't get any attendance link.
Okay, ma'am. Actually, we have a
Mm-hmm.
software which automatically record your
Okay,
attendance.
from
So
meeting
based on the
attendance,
software,
right?
yes.
Okay.
So definitely we
And
are going to send to.
I think it's organized from ATAL. So we need to give any attendance in ATAL site.
Actually, the attendance we will be submitting to ATAL, and ATAL will be giving you the certificate.
Yeah, sure. Yeah. Okay, so we need not to update anything in the this
No, ma'am.
ATAL site, right? Okay.
One thing you need to do after this FDP overs, you
Yes,
need to
yes.
go on ATAL portal and give the feedback. That's all. After the feedback, you'll
Yes,
get your
that is the
certificate.
end of the day, I think.
After the Friday, maybe you can go give that feedback on Saturday.
Yes, yes. Actually, in the today's morning session, I had some issues with network. So I maybe I don't know whether you will get it or not. But I disconnected many times.
And no problem, ma'am. We have the facility that it can monitor that whether you have attended or not.
Okay. Thank
There is
you.
no problem at all.
Yeah. Thank you.
Sir, can I audible, sir?
Yes, ma'am. Yes, sir.
Sir, actually morning you were told that the exam is there. Okay, that
Yes,
60%,
yes. Actually,
60% up to secure. But the thing is that, sir, it is only for one time, or if he's not got first time 60%, he can go for second time attempt also.
okay, sir. What we got AICT ATAL, the both things we got. We have also programs for the coordinator. So there we got that 80% attendance and 60% marks from the test.
Yes, yes. My question is,
Yes, sir.
we can attempt several times if the exam we are not attend at the 60%. That is my question.
Your question is whether for the first attempt or you need to have the second attempt, right?
Yes, yes. I can go for second attempt or not?
Okay, sir. For that, I'm not sure, but still I can ask the AICT people.
Okay, okay, sir. Okay, sir.
So I guess there is no more question. If there are questions,